This is a lecture on energy and nuclear power. It goes along with chapter 15, sections 1 and 5. So let's get started. Here's our important vocabulary for the unit. We won't really be talking about the Curie or this word right here that I can't pronounce, but those are units for nuclear power. We'll talk about those in class, not in this lecture. There will be a outline that is on Schoology for you to use as you take your notes for this unit. All right, so just as a reminder, a system is a set of connected parts forming a complex unit. So a great example of that is my classroom or a nuclear reactor. So a nuclear reactor has a lot of parts that are moving together, and together they form a system. When a system works, it can either have a positive feedback or a negative feedback loop. When you have that positive feedback, it continues with the same consequence or reaction in the same direction. So here we have the increasing amount of CO2 or carbon dioxide, which leads to global warming or global climate change, which increases evaporation, which increases water vapor, which increases evaporation, which increases water vapor, which forms our atmosphere. So that is a positive feedback loop, whereas a negative feedback loop is a different consequence or a change in the system. So when we're thinking about systems, all of our systems are going to have some sort of complexity, and maintaining this complexity is going to require energy. There's going to be two different types of complexity that we have, and this is laminar and turbulent. So if you think of a match and you light it on fire and then you blow it out, you'll have your laminar flow at first and then your turbulent flow. That is the energy going from something that is less complex to more complex, so less chaotic to more chaotic. And as we start to lose energy or even gain energy, we're going to increase chaos. So this is kind of also the idea of entropy in a system whenever we are using energy. So what is that idea of energy in a system? Well, energy is just the ability to do work. So we have energy in many different forms, like heat, light, motion, electrochemical, and gravity, also nuclear. And we have two major types. The first is potential, which is just stored energy, and then the second is kinetic, which is working energy or motion energy. And there's also chemical energy, which is at the molecular level. So that would be like you ate food for breakfast, and then it transfers to kinetic energy when you are walking the hallways at school. Energy is important when we're thinking about this idea of thermodynamics. Heat is the transfer of energy from one system to another. Any system with energy will have heat. So there will be heat in any system on Earth or in the universe. Even in the voids of space where there is no air, there will be some sort of heat because there's some sort of energy there. And if we're thinking about this, if a system does work, so remember that work is your force times distance, heat will be the results. And if we're thinking about these, that energy is going to follow two major laws, and those are the first and second laws of thermodynamics. So that first law of thermodynamics is also called the law of conservation of energy, which means that we cannot create or destroy energy. So in our universe, we have already a set amount of energy and we cannot create or destroy it, but it can be converted from one form to another. So like I said earlier, you convert chemical energy that you get from your food at the molecular level to kinetic energy when you move around every day. And then that second law of thermodynamics is energy will degrade with use. So you cannot go back to high quality energy when you use it. So it will go from a useful form to a less useful form. And this is going to create this idea of entropy right here. Entropy is basically disorder or chaos, and that just means that your energy quality has been depleted. So we're thinking about that smoke again. So, for example, if we're going back to that nuclear power plant, we have the high quality energy in the form of uranium-235 or uranium fuel, right here in the center of our containment building. And then that energy is going to be transferred to water, which is right out here. So we have our reaction taking place inside of this little vessel here. And when the reaction occurs, it heats up water in here, which generates steam. So the energy is now transferred to steam. That steam moves through and turns this turbine. So now we're transferring the energy to this turbine. The turbine spins, and then that energy is now transferred to the generator, then to the transformer, and then to you all at home to charge your electronics. So we have just used the second and first law of thermodynamics. So energy was not destroyed, just transferred from nuclear to thermal in the form of heat to mechanical to electric energy. And then we started with that nice high quality uranium fuel, and then we left off as water vapor in the very end, and that's our low quality fuel. We can't just go back to that high quality uranium fuel. So speaking of that, energy has quality, and that's going to be the basically the capacity for our energy resource or anything to put out useful work. So we have high quality energy and we have low quality energy. So this is a picture of different types of coal. Anthracite is a high quality energy coal, whereas lignite is a low quality energy coal. So we're going to get a lot more work out of our anthracite than we are going to out of our lignite. So in the end, when we're thinking about our energy resources, we are most concerned with the net energy because that is what's going to incorporate the energy needed to obtain an energy resource. And what that means is the high quality energy needed to extract or obtain your energy resource. So for example, because there is not a lot of energy needed to mine, transport, and burn coal, so it has a high net energy yield. So basically, the energy that coal generates is a lot higher than the energy needed to obtain coal. But we're also thinking here about the energy return on investment. So this is in contrast to the costs that are involved with the extraction and obtaining of the resource. So it has a very high net energy yield and a high energy return on investment. But if it doesn't have a high net energy yield or a good energy return on investment, then the government will utilize subsidies in order to make it more competitive, the energy resource more competitive in the market. So net energy and EROI are important for economics, but also they're important for environmental reasons. So if a energy resource has a higher net energy yield, we are more likely to use it in the market because it is going to be the cheapest option with the greatest amount of energy. So this is typically why we see fossil fuels used more often for our energy resources than our renewable resources, because our renewable resources are generally a lower net energy yield in the end. So here is our nuclear power plant again. So because we need all of that money and all of that energy to extract, enrich, and then transport, store, all of those things, store the waste, all of those things over the lifetime of a nuclear power plant, it has a very low net energy yield. It's also very, very expensive to maintain this nuclear power plant. It's expensive to enrich uranium. So the government does rely on subsidies to keep the cost down and to keep it competitive in the market. So when we're thinking about energy, ultimately we're thinking about these two math equations, work equals force times distance, and we're going to be mostly concerned about the unit joule. But you can also use the Newton meter. The other equation is power equals work divided by time, which we'll use the watt for, which is equal to 1 joule per second, and you will have to be able to convert between watt and joule per second. So these are things that you need to memorize and know, but there are a lot more equations that come with this energy unit, so make sure you're getting these down now. So let's talk about nuclear power. So before I talk about any energy resource, when we are creating electrical energy, there is a process that goes along with almost every single resource. The first thing is we're going to obtain that resource. All right. The second is we're going to burn that resource to boil water. When we boil water, it's going to create steam, and the steam is going to rise because of convection. Steam is going to turn a turbine, which is basically like a big kind of fan-shaped thing, which is above the boiling water, or the steam will move through a series of pipes to the turbine to turn it. The turbine will spin, generating electricity through a generator, and then the electricity is sent to the power grid. The power grid is basically what everybody is connected to, the school, houses, everything. When you are on the power grid, you are paying utilities through Virginia Dominion Power, so we are all connected to the power grid. So, for example, we have a uranium fuel here. We're heating the water. It goes through this pipe. The steam goes through the pipe, spins the turbine, generates, or goes to the generator to generate electricity, and then it goes off to the power grid to create electricity. So what is nuclear power? When we are thinking about nuclear power, we're thinking about this isotope of uranium. So uranium is an ore mineral that is obtained through mining. We utilize both surface and subsurface mining to get to our uranium, which is found in rocks. It's a very, very involved physical and chemical process in order to do this thing called uranium enrichment, which is basically taking that uranium, going through a bunch of different chemistry steps, and increasing the uranium-235 concentration to 3 to 5% from a 0.7% concentration. An isotope is a form of an element with a different number of neutrons in the nuclei from that normal element that we see on the periodic table. So when we have U-238, we have 146 neutrons and 92 protons, whereas U-235 is going to have 143 neutrons and 92 protons. In the end, we're looking for this thing called uranium dioxide, or UO2, and that is going to be packed into fuel rods. These little pellets are about the size of a pencil eraser, so they're really tiny, but they hold so much energy. And about 30 of those fuel rods are packed together to create a fuel assembly. After you create a fuel assembly, they are shipped to our nuclear power plant. So this is done off-site, and then they are brought to a nuclear power plant. We have we have a couple different types of nuclear power plants, but two that we're going to talk about. The first one is an LWR, pressurized or light water reactor, and this is just using normal water in order to create energy. So we're just boiling that water, using that steam to create energy. If we use something called heavy water, which again we're using an isotope of water or hydrogen, which is called deuterium. So hydrogen in its nucleus just has one proton. Deuterium is going to have a proton and a neutron. If we're using that heavy water, it's going to be called a heavy water reactor. Now, the difference between these two is that a light water reactor is going to have a separate chamber to pressurize our water or our steam, whereas a heavy water reactor, the pressurization can just happen all in the same area as our fuel cell. So what is going to happen is when we have those fuel rods, which are packed with that uranium dioxide, they are placed into our reactor with these things called control rods. And our control rods are just going to be made of elements that are mostly metals that can absorb our extra neutrons, because we're going to have a fission reaction that takes place. So basically what we're doing is we're splitting those uranium atoms and we're releasing energy that way. So the neutrons are going to go flying out, and they're going to be the control rods are going to absorb those neutrons in order to kind of create a safer environment. While this is occurring, coolant is going to be flushed around our fuel rods and our control rods in order to cool down our system, because this is going to create a whole lot of heat. Most of the time when we have a nuclear meltdown, it's because of the lack of some sort of coolant. So we're using coolant, which is most of the time water, in order to absorb that excess heat. And after a while, that water is then pumped into something called a cooling pond. All of this is contained in concrete called a containment shell, just in case of a meltdown. So we have something called our nuclear fuel cycle, which is outlined here. Most of our nuclear power plants can only last 60 years, but our nuclear fuel cycle is going to include the extraction of our uranium. It's going to include the enrichment of the uranium, the usage of the uranium, and then eventually the decommissioning of our reactor. When we decommission a nuclear power plant, we have to go through and we have to sanitize the entire power plant, because the materials that are within it have been exposed to radiation. All right, so let's talk about some environmental issues associated with nuclear power. The first one, the first positive thing about nuclear power is that there is no carbon dioxide generation in the creation of energy with nuclear power. Now, when I say that, there is carbon dioxide generation in the transfer of fuel rods from the mine to the enrichment place to the reactor. So we do use trucks in order to get from point A to point B to point C. But when we are just creating our energy here, there is absolutely no carbon dioxide that is released out into the air. It's only water vapor. However, we do have to deal with this thing called thermal pollution from the cooling of the water. So if we look back at this picture, we're releasing water into our cooling pond over here. If you've ever been to Lake Anna, this is a cooling pond, a very large cooling pond for the North Anna nuclear power plant. And when we have excess heat going into a lake or body of water like this, it decreases something called dissolved oxygen in the water. So fish breathe oxygen in the water. It's actually dissolved in the water, and they take that in through their gills in order to get their oxygen to breathe. And they like to have a high amount of dissolved oxygen in the water. Like we like to have the correct amount of oxygen on land. Well, the relationship between dissolved oxygen and temperature is that the lower the temperature, the higher the dissolved oxygen will be. So when we see this, see a good correlation between low temperature and dissolved oxygen, we'll see some really nice critters like largemouth bass and bluegill and perch. But when we have a nuclear power plant where we're in an area where thermal pollution is affecting it, we are more likely to have invasive species in the area. So if you have been to Lake Anna, you probably have seen this plant right here. It's called hydrilla. It'll get caught up in your boat motor. It is very, very invasive. The second big issue with nuclear power is the waste. So when the fuel is used up in a fuel rod, it is something called spent. So those spent fuel rods are actually stored in a nuclear power plant, and we put them in a bucket of water, basically, or a big tank of water, and then we move them into something called a cask. We don't know how long a cask can hold a spent fuel rod. It could be 10 years, it could be 100 years. We're not really sure what is safe yet. But after that, and after the power plant has been decommissioned, what do we do with a fuel rod or radioactive material that takes 700 million years to complete one half-life? Well, the government has created this thing called WIP, or the Waste Isolation Pilot Plant, which is located in New Mexico. And they've also talked about things called geologic repositories. One of the most famous one is Yucca Mountain. This is not a place yet, so this is just being talked about as far as a geologic repository for our nuclear waste. We are not sending our stuff there yet, however. But people in Nevada are throwing out this word NIMBY, or not in my backyard, because who would want a bunch of nuclear waste close to them? Most of our power plants were built in the 1970s with a lifespan of 60 years. We are going to have to think about what we're going to do with this stuff very, very soon, because those plants are going to start to be decommissioned. So, speaking of our power plants, we do have a couple of nuclear meltdowns that have occurred in the history of nuclear power usage. The three most significant are 3 Mile Isle, Chernobyl, and then Fukushima Daiichi. The first is 3 Mile Isle, which occurred in 1978 in Pennsylvania. This is really the only big one in the United States, and this was just a partial meltdown. So here's a picture of it right here. This one was just an operator's error. They did not allow the correct amount of coolant to get to the system, resulting in a partial meltdown. 3 Mile Isle nuclear power plant still is in operation today. The second one in 1986 was Chernobyl, and this is considered the worst nuclear accident in history. Again, we starved the system of the coolant, which resulted in a gigantic explosion, and we did have to relocate 220,000 people. They're considering Chernobyl a positive feedback loop, because the reaction that occurred just kept getting worse and worse and worse and worse and worse as the fission process continued. And the most recent one was Fukushima Daiichi. This was not operator error. It was building constructor error, because they did not take into the account that they were on a giant subduction fault line, and they should have probably taken in a little bit more precautions when creating a nuclear power plant here. But basically, an earthquake generated this tsunami. Remember that a tsunami is a wave that comes onto shore from the ocean, and then the tsunami's water shut down the backup generator, stopped the coolant, and then caused an explosion. And we did have to relocate 500,000 people for this nuclear meltdown. So here's what the explosion looked like, and we do have to worry about something called nuclear fallout when we have a meltdown. So you'll notice that this fallout map does cover the United States, and this is because when a nuclear meltdown occurs, it comes up into the atmosphere, and atmospheric conditions will bring it over into the United States. This is not something that will really harm us, but it is kind of interesting to look at. You have to wonder what the implications will be like on the critters in the oceans. Now today they are going back and they're looking at the effects on the local wildlife, so they're not quite sure if these little daisies are the result of nuclear radiation or if it's just an imbalance of hormones, but it could be a result of nuclear radiation. But all of this new research on something so recent has allowed us to create better, or will allow us to create better nuclear fallout maps in the future. So, weighing the pros and cons of nuclear power, not a lot of pollution in the creation of energy, specifically CO2 in comparison to other resources. Remember that we do have CO2 in the transportation of the uranium from the mining site to the enrichment site to the reactor site. We have a very low risk of accidents, and we do get a lot of energy. On the other hand, we have a ton of disadvantages. First and foremost, it's non-renewable. Second, we have that low net energy yield with a high cost. We have radioactive waste that we're not really quite sure what to do yet. We have mining and thermal pollution, the threats of nuclear weaponry, and then, whoops, that's an advantage. Advantage is that it will decrease reliance on oil imports. All right.